The next part of this sort of double bill. This will be the validate package, also from people from Statistics Netherlands, which seems to be very active in the R sphere, and you'll have noticed the invitation to the meeting on official date. What's the meeting that you're? It's in November, October?
In September.
In September, yeah. So that's something, and everybody working in official statistics probably should at least consider applying now to get there. And
they sure should.
Yeah, good. Edwin de Jonge, you continue with something which has already been mentioned, which is validate tools. Okay, you're welcome.
Presentation. I'm going to talk about validate tools, and I'm a colleague of Mark, and together we wrote this book. So I'm a data scientist or methodologist at our bureau, Statistics Netherlands. So we're the official bureau making all official statistics of the Netherlands. I'm an author of several packages, and I'm a co-author of this book Mark just presented. So I'm going to talk about data cleaning. I'm curious to know who has to do some data cleaning in his daily job. So could I see some hands? Yeah, that's almost everyone. Yeah, that's also my experience. And also, at a larger scale, about 80% of our job as an official statistics bureau is data cleaning. So getting our data in the right shape, in the right form, removing errors, filling in the gaps, that's all the things we need to do. And luckily there are a lot of data packages or R packages nowadays that can help you in this task. So for example, the tidyverse is very good at getting your data in the right shape, in manipulating it, in transforming it. Also, on this conference, the recipes package was presented, showing how you derive a nice data matrix to get your regression going. There are also some packages checking your data, because data has to be valid. So it can contain all kinds of errors or missing values. And luckily, there are a couple of packages for that. So one is validate, which I will shortly introduce later on. Another one is datamate, which checks your data in all kinds of ways, can help check your data in all kinds of ways. Another one is error locate, by looking at where the errors in your data are. And if your data has checked or errors have been removed, you often have to impute values, because you want to have as much data as possible. In extreme cases, removal of errors can result in no data at all. So there are a couple of packages again with that. So FIM can be used to assess missing values, for example, and both simputation and recipes have methods for imputing data in a very elegant way. Mark just showed you some methods to do this in a couple of lines to impute your data in a very organized, structured way. The other thing, Mark just showed you how to track data changes and improvements. So ideally, you would want to have properties of your data cleaning process where you can be reproducible. And this is even more true for our business. We make statistics on a monthly basis or a quarterly basis or a yearly basis. And then each time we have the same process: collect data, clean it, analyze it, and publish it. So we want to be reproducible, and each analysis and data cleaning step should be as much as possible the same as the previous one. So there are a couple of ways of doing it, but there's one thing I think everybody uses, but not in an explicit way. So the thing we do and use in our packages is using data rules. So specifying what your data is about. This actually domain knowledge. So our data cleaning philosophy is explicit is better than implicit. So often you encode these rules within your data. So you do all kinds of assertions or checks on your data, and maybe you remove some data if these assertions are true or false. And often we see in our kind of work that there's a lot of domain knowledge. So which values cannot be true at all or should be true, and we try to encode them into data rules. So R statements specifying if the data should conform to it or not. And we store them explicitly, so as a separate R file with these data in these rules in it. And this has several advantages. So you can do easy checking on it. I will show a short example later on. You can also make some statistics on the data quality itself. You can try to find out how often is a rule violated, for example. How many records are wrong? How often is a variable wrong? And how does it affect your final result? So we wrote a while back the package validate. And validate allows you to formulate these explicit rules that data can conform to. So this is a very simplistic example I have right here. I have a data frame with just one record. Age is 160, job is no, income is 3,000. And you can see that this record is invalid by definition because I have some extra rules. I clearly define that age should be more than 0 or equal to 0. It should be less than 150. Job should be yes or no. If job is yes, age should be over 16. And if income is over 0 or larger than 0, job should be yes. So you specify this set of domain knowledge about the real world, and you can apply this to the data. And a lot of our packages work with these kind of rules. So you specify the rules at only one time, and then you apply them in certain settings. So validate checks these errors, but it can also provide all kinds of statistics on them. Error locate uses these rules to locate which of the variables are wrong or not. And we have also all kinds of bit nifty data correction methods trying to manipulate the data as little as possible so it conforms to the rules you have specified on the data. So if we have all these tools, why do we need validate tools? Well, that's a bit of second generation or more. If you have many rules, which happens to be in our case, so some of our statistics have over 100 rules or 200 or 300 kind of rules. So you have a large system with many rules defined, and these rules interact. They're not independent of each other, they have connections. And sometimes there are contradictions in these rule sets. So you have quite a large rule set, and then you want to see how you can simplify and detect contradictions in there. Sometimes rules are redundant, so they define there are multiple definitions of the same rule, or one rule is better than the other ones, and you want to clean up your data set, your rule set. So we like to do this, and this is done using formal logic. You don't have to do formal logic yourself if you use validate tools. It's all done for you, and it's just a fun problem to solve. So one of the things that can happen is that you have two conflicting rules. And it might seem strange, but in practice it happens. If you have many, many rules and many, many people are working on this data rules on this rule set, it sometimes happens that people declare contradictory rules. So again, a very simplistic example. Suppose we have a rule that the data should be over 21. But there is another rule stating that age should be less than 18. So this is a rule set, so it means either rule 1 is true or either rule 2 is true, not both. So you have a contradiction. So luckily, the validate package has a function called isInfeasible, which checks if your rule set is infeasible or not. In this case, it's infeasible, so there are contradictions. And now, well, you have a contradiction in your rule set, and now you have to resolve this conflict. And luckily, again, you can resolve this by using two extra methods called detect infeasible rules, which will return one or more rules which make the rule set infeasible. So if you remove these rules, the rule set will be feasible again. But you would like to know what the conflicting rule is, because the rules that are in conflict, you have to make a choice which one you want to keep and which one do you want to remove. In this case, you can detect what the contradictory rule is by using is contradicted by, and you can see that either rule 1 or rule 2 has to be removed. Which one is up to the human being? Another functionality of the package is to remove redundant rules. So for example, suppose we have rule 1, h should be over 18, rule 2 says h should be over 12. Rule 1 implies rule 2. So you can detect which rule are superfluous with detect redundancies, and you can also remove redundancies. So if you apply this on the rule set, you will end up with a removed rule set. So as you can see in the sheet or on the slide, that remove redundancy removes rule 2. And another thing, what often happens is that you want to substitute values. So for example, I have this rule set: if gender is male, weight should be over 50, and gender should be either male or female. I can substitute one value or one or more values into this rule system, making these variables constants instead of variables, and then the rules will be collapsed or will be simplified into simpler rules. So weight should be over 50 and gender should be male. And this is often useful because in our practice we have often very complex rule systems with many diverse subpopulations describing all kinds of different rule sets, and often helps to specify just what subpopulation would to describe. Using again the same conditional logic, you can do all kinds of neat stuff like this one. This is a bit more complex or complicated, but still classical logic. So for example, if income is over 0, age should be more than 16. So if one has an income, he should be at least 16 years old. But there is a conflicting rule, or it's not a conflicting rule, by the way. There's another rule saying age should be less than 12. So you can make this more simple by so the first rule can be rewritten in that case. So you know that if income larger than 0 implies age should be over 16. Age cannot be over 16 because age has to be less than 12. So income should be 0 or less. And the system automatically derives this. So it detects all kinds of inconsistencies and tries to resolve this. And you can end up with a much simpler rule set, which you can use to check your data again. And of course, we want to make it as easy as possible, so you don't have to call all these rules yourselves. There's just one overall rule called simplify rules, and it does everything you would like to do it. So, for example, if you have this rule that we have a job, should be yes or no. If job is yes, income should be over 0. If age is less than 16, income should be equals 0. This defines a rule system, and there are also implied rules. So the implied rule over here is that you cannot have a job when you're less than 16 years old. It's not explicitly stated in the rules, but that's the consequence of this combination of rules. So let's fill in or fixate job to yes, and then the rule system collapses into very simple rules that income should be over 0, age should be more than 16, and job should be yes. So this helps us a lot in practice to keep our rules to consistent and to as simple as possible. So how does it work? Well, we parse these expressions, our expressions, and reformulate them into formal logic form, and then translate these into a mixed integer problem. So for each of these problems, where there can be an inconsistency or a redundancy or an implication or a partial contradiction, we translate this into a mixed integer problem, and we use a mixed integer programming solver to resolve this problem. It doesn't work for all rules, so the examples I've shown are for rules using linear restrictions, categorical restrictions, or if statements using combinations of these two. And an if statement can be written into a logical form, which is also classical logic. So an if statement can be written into an OR statement. So if you have P is true, then Q is true. Otherwise said, P implies Q, can be written in the form either P is false or Q must be true. And we rewrite every if statement in this manner and then translate this into a mixed integer problem and solve this. So for example, this one, if we have the if job is yes and income is over 0, internally this is translated into job is not yes or income is over 0. And you can see this if you print the rules, then you can see the other formulation of the rules. So they have a nice form, the rules, but they have also an internal logical form, which are OR statements or AND statements. So if you're interested more in the theory behind this, well, there's a chapter on that in our book. And I'm happy to hear your questions if you have any.
Okay, thank you very much, and thank you for keeping to time. Questions?
Over there.
Yeah.
Thank you very much for the nice talk. I really like the package. And I was wondering whether this package is scalable, and also if the user can decide whether one rule can override another rule.
Good question. With scalable, you mean can it handle large rule sets? Well, we've tested it with till 100 rules, but it's a complicated question you're asking. It depends on how complex the rules are, so how many nested statements there are in these rules, and but we didn't run in any problems yet. So I'm curious to know if you have in your practice have large rule sets and if you run into problems or not. If you do so, please let me know. The second question was about overriding rules. That's a good one. For now, rules are hard rules, meaning data has to conform to this rule. We are looking into offering weights to the rules, so the rules become a bit more soft, so they can be partially true or not. Yeah.
Hi, thank you very much. Can it be integrated with testnet and checkmate?
That's a good question. I haven't looked into it, so but I will. But there is a difference. So testnet and testnet checks if something fails or not. So the result is that it's a bit of a different design philosophy. So, and also for assert that and other packages, they just check if your data obeys, and if not, you're in trouble. You have to resolve it. With validate tools, you use these tools to check if it is it valid or not, but you also have some statistics on which records are not valid or not. So you can also see how often it occurs, what you should do to remove it or not. So that's a bit of a different philosophy. So with assert that and test that, you want to make your data or your program as solid as possible. But if it fails, you have to repair it somehow. But with this, the design philosophy is a bit different. But you could make, I think, a test that or checkmate thing where you test for the rules, and then if it doesn't obey, you fail. That's possible. Yeah.
Okay. Any other questions, or should we take the coffee break? Coffee break. Okay. Welcome back in 25 minutes, and thank you very much.